You ever wonder how pigeons find their way home from hundreds of miles away? Or how monarch butterflies and sea turtles navigate perfectly across these massive, featureless oceans without a map? It's an incredible mystery, right? But the answer, it isn't magic. It's physics. These creatures are literally sensing an invisible force that completely surrounds our entire planet. Welcome back, Focus learners, to another explainer. Today, we're unlocking the invisible. We're diving straight into Unit 5 of Grade 10 Physics, which is all about the absolutely fascinating world of magnetism. We're going to break down the whole shebang, from the simple magnets holding up your grocery list to the invisible fields protecting the Earth from deep space. Okay, let's look at our roadmap for today. We'll kick things off with the magic of magnets, map out those invisible fields, and explore Earth as a giant magnet. Then we hit the big plot twist, uniting electricity and magnetism. We'll wrap up by looking at the magnetic force and, finally, how magnets actually work in the real world. Let's get started. Section 1. The magic of magnets. From ancient stones to refrigerator doors, let's ground this complex physics in something you've probably played with since you were a kid. So, the story of magnetism actually kicks off thousands of years ago. The ancient Greeks stumbled upon these naturally occurring stones that had this wild ability to attract iron and nickel. They called this stuff lodestone, which is basically a magnetized form of an iron oxide mineral called magnetite. And honestly, that one simple observation, it completely laid the groundwork for everything we know about magnetism today. But what exactly is a magnet? Well, by definition, it's a material or object that produces an invisible magnetic field. And it's this specific field that's responsible for the force that pulls or attracts other materials, specifically metals like iron or steel. And this brings us to the three main types of magnets we interact with all the time. First up, permanent magnets, think steel, which basically hold on to their magnetic properties long term. Then you've got temporary magnets, like a paper clip or an iron nail, which only act like magnets when they're actively hanging out inside a magnetic field. Finally, electromagnets. These generate a magnetic field using a coil of wire that's conducting an electric current. But here's the golden rule for all of them. They all have a north and a south pole. And, as you've probably heard a million times, like poles repel and opposites attract. Moving to Section 2, mapping the invisible field, visualizing the unseen. Now that we have our physical magnets, let's look at the invisible forces they project into the space around them. Okay, so how do we actually see an invisible field? We use magnetic field lines. Imagine shaking a bunch of iron filings over a piece of paper with a bar magnet underneath. You'd instantly see those filings snap into these beautifully distinct pathways. Now, these lines follow some strict rules. They absolutely never cross or intersect, ever. They form continuous closed loops, and outside the magnet, they always point from north to south. Also, the denser or closer together those lines are, that means you've got a stronger magnetic field right in that exact spot. Now, here is where things get super interesting. There is a massive difference between electric fields and magnetic fields. In electricity, you can have a positive or negative charge totally chilling on its own. But in magnetism, no way. North and south poles are a package deal. If you were to snap a bar magnet perfectly in half, you don't get a solo north and a solo south. You literally just get two smaller magnets, each with its own north and south. A solitary magnetic pole, a magnetic monopole, has absolutely never been observed in nature. Section 3. Earth, the giant magnet. The planetary scale. We're going to drastically zoom out now to see how our entire world operates, just like those bar magnets we were just talking about. Deep, deep beneath our feet, in the Earth's outer core, there's this massive, swirling ocean of molten iron. The movement of this liquid metal essentially acts like a giant dynamo, and it generates a colossal geomagnetic field that reaches way out into space. This invisible shield is exactly what protects us from harsh solar radiation. And yep, it's the exact same field those birds and turtles are tapping into to navigate. This leads to a really fun quirk about how our compasses actually work. We all know a compass needle points north, right? But remember our golden rule, opposite poles attract? So that means the north pole of your compass needle is actually being attracted to a magnetic south pole. Yep, the spot at the top of the globe that we geographically call the North Pole actually behaves like the south pole of a giant bar magnet. Kind of blows your mind a little, doesn't it? All right, Section 4, electricity and magnetism unite. Here comes the plot twist, and honestly, this changed the course of human history. For the longest time, scientists thought electricity and magnetism were completely unrelated, totally separate things, but they aren't. Magnetism isn't just trapped in special stones. Actually, anytime an electric charge moves, like electrons zipping through a copper wire, it actively produces its own magnetic field right around that wire. Electricity and magnetism, literally two sides of the exact same coin. To figure out the shape of this field, physicists use a trick called the right hand rule. I want you to literally do this with me right now. Hold up your right hand, point your thumb in the direction the current is flowing through a wire. Got it? Now curl your fingers inward, like you're gripping that wire. The circular direction your fingers are curling, that perfectly maps out the invisible magnetic field lines wrapping around the current. It's such a brilliant, simple way to visualize the physics. Section 5, the magnetic force. The push and pull of moving charges. Let's see how this builds into actual physical force.
So we know a moving charge creates a magnetic field. But what happens if you take a moving charged particle and just launch it directly into a magnetic field that's already there?
Well, it gets pushed. It experiences a magnetic force. Now, please don't get bogged down by the textbook math here. Just look at the relationships. The physical push gets bigger if the particle has a larger charge, if it's moving faster, or if it hits a stronger magnetic field. Simple enough, right? But the real kicker is the angle. If the particle is moving perfectly parallel to the magnetic field lines, the force is exactly zero, nothing. But if it crosses those lines perpendicularly, boom, it experiences the absolute maximum force possible.
Just to give you some perspective on scale, we measure magnetic field strength in Teslas. The tiny number you see here, 5 times 10 to the negative 5 Teslas, that is the strength of the Earth's magnetic field right on its surface. It's incredibly weak. I mean, compare that to a strong permanent magnet you might find in a lab, which is about 2 Teslas. That is a gigantic difference in scale, and yet Earth's tiny field is enough to span the entire globe and guide a compass.
And this force isn't just acting on single floating particles. Imagine you have 2 parallel wires, both carrying electric currents. Their magnetic fields are going to interact. But pay close attention here, because it feels a bit backwards. If the currents in the 2 wires are flowing in the same direction, the magnetic force pulls the wires together. They attract. But if they flow in opposite directions, the magnetic force pushes them apart. They repel. It's literally the exact opposite of the like poles repel rule we learned earlier for permanent magnets. Finally, Section 6, magnets in the real world. Why this actually matters. All this theory is fascinating, but how does it impact your daily life? The concepts from this grade 10 unit literally power modern civilization. In medicine, MRI machines use magnets thousands of times stronger than your fridge magnets to safely peer inside the human body. In tech, traditional computer hard drives store your photos and data by altering tiny magnetic segments on a spinning disk. In industry, massive electromagnets, which we can just flick on and off by changing the current, lift tons of scrap metal at a time. And of course, simple compasses are still out there, aligning with Earth's field to help us navigate the physical world. We've seen how stones attract metal, how the Earth acts as a giant shield, and how moving electrons conjure up invisible fields that run our world. But it leaves us with this final thought for you to chew on. If electricity and magnetism, 2 things that seem so completely different, are actually just 2 sides of the exact same invisible force, what else in our universe is secretly connected, just waiting for us to discover it? Thank you for exploring the invisible with me today. Keep asking questions, and I'll catch you in the next explainer.